Universidad Autónoma de Madrid. She did her master's in theoretical chemistry at the Universidad Autónoma de Madrid too, and also her PhD in theoretical chemistry. So she was a postdoctoral research fellow in the Department of Physics and Astronomy at the University College London. And currently, she is a senior lecturer in the School of Physical Sciences at the Open University in the UK. She is also the vice chair of the Commission on Atomic, Molecular and Optical Physics of the International Union of Pure and Applied Physics, UPAP. And in today's talk, Professor Jimena will present the seminar entitled How to Model Low-Energy Electron Scattering from Molecules and Why It Matters. So, Professor Jimena, thank you so much for accepting our invitation, and the word is yours.
Thank you, and thank you for inviting me. It's nice to be in Brazil, even if it's remotely. So let me tell you what I want to tell you about today is the work that I do. So I study computationally and theoretically low energy electron collisions with molecules. Now, why study this? What is it about these processes that one wants to know about? So let's remind ourselves what a scattering process of a collision is. So in a collision can be defined as a process in which moving particles are forced to deviate from their initial trajectory. So if we have an electron and a molecule, we normally assume the molecule is not moving and the electron comes in and it's diverted by its interaction from the molecule. Now, the interaction between the projectile and the target, the electron and the molecule, can lead to changes in the internal structure of the particles, in this case, the internal structure of the molecule. So when we say we want to study electron-molecule collision, what we want to understand and quantify is both the changes in direction and the potential changes to the internal state of the molecule. One of the important points here, and the reason why describing collisions is harder than, for example, describing bound states of systems, is that this process involves the continuum, electronic, and occasionally the continuum of the nuclear degrees of freedom as well. So why we study these processes, why are they important? Well, because of their applied relevance on one hand, and this is because there are a lot of environments in which you have free electrons and molecules, and I will mention a few in my next slide. And that means that if you want to model those environments to perhaps predict their behavior, you need quantitative data on all the possible processes that can take place. And that quantitative data is normally provided in the shape of cross-sections. So many of you would have studied in your undergraduate studies what a cross-section are, and you would have looked at the Beer-Lambert law, and the cross-section can be seen as an effective area that is provided by the target to an incoming projectile for a specific process. So we quantify the likelihood of a process taking place with the cross-sections. Now, these processes, collision processes, not only have applied relevance, but they're also of fundamental interest. So the purely quantum mechanical phenomena at this low energy that I will define in a moment, that are useful, are interesting to investigate. And finally, there are synergies in the sense that if you develop methodology and software, which is what I do to study electron-molecule collisions, these tools can be adapted to study, for example, positron scattering. Positron is the antiparticle of the electron. Photoionization, which can be seen as half a collision. Strong field physics, for example, the effect of ultra-short laser pulses on molecules, and also processes that are mediated via the formation of temporary states of resonances, like, for example, associative detachment, etc. So let me briefly tell you about the applied relevance of these cross-sections, or these data. So wherever you have a plasma, you're likely to have free electrons and molecules. So wherever you use plasmas, for example, when you make microchips with plasma etching, or when you make other small things with nanofabrication, for example, with focused electron beam induced deposition, or if you use plasmas for medical purposes, if you want to model this, you need cross-section information. The other use that is very important is in medicine. Because if you have ionizing radiation, which is the kind of radiation that you will use, for example, in radiotherapy to treat cancers, or for imaging. These ionizing radiation will produce free electrons, and many of these free electrons have low energies, and they go to interact with other molecules in the medium. So if you want to quantify, for example, how the energy of this ionizing radiation is deposited in the cell, you need information on the interactions of electrons with the molecules. And this kind of radiation-induced damage is not only important in a biological context, but for example, if you're using X-rays to image, for example, a molecule, these X-rays have enough energy to ionize the molecule, and you will have electrons that are free and are likely to cause damage to the thing that you're trying to image. So that is important to understand as well. Now, before I move on, let's remind ourselves of what kind of processes are possible when you have an electron interacting with a molecule. The simplest one is elastic scattering, where the molecule isn't changed, but you may have changes to the direction of the projectile of the electron. Then as you increase the energy, you will have changes to the internal state of the molecule, so you can change the rotational states, the vibrational states, or the electronic states. If you excite the molecule into a vibrationally dissociative state or an electronically dissociative state, you may have impact dissociation. And if you go still further in energy, you may have enough energy to ionize your molecule and end up with a cation. There are processes that can take place that I haven't listed here, but I would mention later on. But the other thing to notice is that these processes can happen in combination. So you can, for example, have ionization dissociation, not ionization and dissociation separately, but together. So there are a lot of processes that can take place, and study them is difficult. I'm going to talk about low energy processes, but if you want to understand these in the applied environments that I mentioned before, you need cross sections for a large range of energies. And what I want to mention is that if you want to provide this information, what you need is a community effort to do this. And there are two examples here. On the left is a paper that I published with a number of colleagues 1 or 2 years ago, trying to provide data for this molecule. You may know some of the people here because they are colleagues from Brazil. And this is another example here on the right. Is a paper published about 10 years ago, where colleagues collated all of the information on electron scattering from carbon monoxide. So here was all of the data of cross sections from between 0.01 electron volts to 1 kilo electron volts from experiments and theory, all that was available at the time. So how does one describe, from a theoretical point of view, low energy electron molecule collisions? What are the approaches that one uses? And in general, these are implemented as computational approaches. Well, there are several, and these have been developed for decades, for more than 40 years in some cases. And these methods are the R-matrix one, which is the one I'm going to tell you about because it's the one I use, the Schwinger multi-channel method with zero potentials, which is developed and used in Brazil, the convariational method that was developed and used in the United States mainly. There was single center expansions. There was a method used in Italy. And then there's more recently, for small molecules, for diatomics, the convergent close coupling approach that is developed in Australia. Now, all of these methods solve the time-independent Schrödinger equation. So you basically have a time-independent Schrödinger equation that you need to solve, where your Hamiltonian describes the state of your target, the kinetic energy of your projectile, and the interaction between your projectile and your target. And you have to solve these subject to the appropriate boundary conditions, as you do every time you solve time-independent Schrödinger equation. Now, what are the difficulties or the challenges in this? Because we're talking about low energies, the detailed characteristics of the target molecule are important. What I mean here is that because we're working at low energies, the projectile will feel, in some sense, the details of the molecular potential. So that means that you cannot use, say, for example, perturbative approaches at these energies. And none of the methods I mentioned before do. Now, we must describe in this case both the states of our target before it interacts. And if you're interested in studying electronic excitation, it's not just the ground state of your molecule, the electronic ground state by the excited states, but we also need to describe the states of the target plus the additional electron, plus the projectile electron. And if you want to describe these states accurately, in a lot of cases, you need to take into account the correlation. You need to describe correlation well. So correlation is an important thing to do. But of course, as I mentioned before, these are systems that involve the continuum. So it's these two things, the description of the continuum and description of correlation that makes the calculations of the modeling difficult. The other thing that is important to take into account is that because in these methods one explicitly or implicitly models both the n electron target states and the n plus 1 electron plus projectile states, these descriptions have to be balanced. Our observables, the cross sections, etc., depend on the relative energies of these states, explicitly or implicitly, and therefore, if we don't get a balance between these calculations, our calculations may be incorrect. So let me tell you a little bit now about the R matrix method, that is the method I use. This is a method that was developed in nuclear physics 70 years ago, probably a bit more, and then translated to atomic and molecular physics to study mainly collision processes and photoionization. The first thing to say is that this method, as many low energy methods, work within what is known as the fixed nuclei approximation. When we're working in an energy range of something like 1 eV, or a bit below, to the ionization thresholds of the molecules, which is of the order of around 10 electron volts, the time of the collision, the time that the electron spends interacting with the molecule, is short enough that the electron experiences, one can say that the electron experiences the molecule fixed in space without rotating or vibrating. So we work within this fixed nuclear approximation, and if you need to take into account, if you want to study processes where the nuclear motion is important, this normally is reintroduced later on. Okay. Now the R matrix method is based in the idea that you can divide space into two regions, an inner region and an outer region, and these are divided by a sphere of a certain radius, A. Okay, and the point is this: what you do is in the inner region, basically, you worry about correlation, and in the outer region, you worry about describing the continuum. So the inner region is the region in which the electron is close enough to the molecule that you cannot distinguish it, your projectile electron, from the electrons in the molecule, and therefore exchange is important and correlation is crucial. Here we use, in general, quantum chemistry approaches, and this is where my chemistry degree has helped me a lot. Now, in the outer region, the electron is sufficiently far away that it's distinguishable from the electrons in the target. And then you can neglect exchange. Correlation is also negligible. What you have is polarization effects, which are much simpler to model. And here you can use single center expansions. You can use approximate descriptions of the interaction potential between your electron and your molecule. And that's the basic idea of the method. Now I'm going to show you a few equations, and for those of you that don't want to follow them, it's the time to go and get yourself a glass of water. But I wanted to give you a little bit more of an idea of what the method entails. So if you're working in this inner region and this outer region, the key of the method, which is summarized in these two equations, is that you have to match the inner region and the outer region solutions. Okay, so you match the solutions, the wave functions, and you match the derivatives. And this is implicitly in these equations because this operator L here is the block operator that has the derivative of the wave functions. And the block operator is introduced if you want to ensure that the Hamiltonian in the inner region is Hermitian. Now, how do you expand the wave functions of the system in the outer region? Well, there it's relatively easy, because what you have is that you can do it as a linear combination of what we call channel wave functions. So these wave functions describe all the states of the target, initial and final, and the state of the scattering electron, which we normally describe in terms of a partial wave expansion, that is, in terms of the angular momentum of the electron. And that linear combination, the coefficients, if you want, are given by the reduced radial functions. And these ones are energy dependent, and they describe the unbound electron. It is these functions that encode the scattering information. Now we know how to do the outer region. How do you do the inner region? Well, in the inner region, we also have an expansion in terms of a different set of functions, and these are what is known as the R matrix basis functions. And these are the eigenfunctions of a Hamiltonian with the block term, so that is Hermitian, in the inner region. So in practice, one doesn't usually have to find these coefficients. It is enough to find the R matrix basis functions. And what can be shown is that if one operates with these, projecting them onto the channel functions and then defining what we call the boundary amplitudes, which are defined here, one can match the reduced radial functions and the derivatives at the boundary between the inner and outer region given by the radius A with the matching is this R matrix that is defined in these terms that depends, it is really a matrix, and it depends on the boundary amplitudes, the energies associated to the R matrix basis functions, and of course, the scattering energy. So it is these terms that allows us to match the inner and the outer region. Now, in practice, what is it that one has to do? The key of describing the physics of the problem well is given for how well one describes the inner region. That's the hard part. That's where all of the real physics of the problem are, in a way. And we have a way of doing this. I'm not going to go into details, but the important point is that what we use is a close coupling expansion that uses target wave functions, uses some wave functions that describe the continuum, the unbound electron, but inside the R matrix sphere, because this is in the inner region, and some other functions that account for correlation and polarization. Now, in the outer region, the problem is much simpler. What one is reduced to do is to solve a set of differential equations that are coupled to get the radial function. And one does that using the R matrix, as I explained before, at the boundary as an initial condition. And then once you've got these radial functions, asymptotically, you can match them to known solutions of the problem, to a known form. And that form is given in terms of the K matrices. And the K matrices are the scattering data that contain the scattering quantities that contain all of the scattering information, and from which one can get cross sections and all other information about the scattering. So, as I said before, these things that nowadays implemented in software, and what with the R matrix method we have done in the UK, and that comes from way before I started this work, is to develop a set of programs to do these calculations. So these programs were started for diatomic molecules back in the 70s, but over the last about decade, we have completely rewritten them, and we've published a paper in 2020 on that, and we make these codes freely available on the internet. You can go to Zenodo and you can download them, and every time we make significant changes or improvements to the codes, we release a new version that can be downloaded for here. And this code can be used to study electron scattering, but also positron scattering without positron information, and photon-induced processes, as I will explain later, if I've got a minute. So let me give you now an idea of some interesting examples of things that we can and do, and things that we cannot do so well, and some interesting processes that we are studying. So the simplest neutral molecule is H2. And you may think that because the study of collisions is decades old, and H2 is the simplest molecule, everything that there is to know about electron scattering from H2 is well known. And the reality is that it is not. For processes like, for example, electronic excitation, we now have, for H2 and for other molecules, excellent agreement between experiment and theory. And the pictures that you can see here are the cross-sections for electronic excitation into this excited state of H2, and these are the angular differential cross-sections. So this is excitation into the same state, but for certain energies that are given here, 17, 20 and 25 eV, what is the angle in which the electron is ejected. And you can see that the agreement of the two calculations, one is the R matrix calculation, that's the black lines, and it's using the method and the codes that I've just mentioned. The calculations are not mine, I'm from the group at UCL of University College London, Jonathan Tennyson. And the other theory is the convergent close coupling, is calculations from Igor Bray's group in Australia. The agreement between the two theories is in general very good, and the agreement with experiment where the data is available, it's also very good. Now, so electronic excitation we can do very well, and I will show you an example later on where we can do it for a much more complicated molecule. But that's a process for which we don't still understand very well how things happen. And to explain that, let me explain to you one of the processes that I missed when I listed what can happen when an electron interacts with a molecule. So this process is known as dissociative electron attachment and happens through the formation of a resonance of a temporary negative ion. So these resonances are metastable states. So the electron comes in, and for certain specific energies, it gets trapped temporarily around the molecule, stays there for a little while, and it can decay this temporary state in two ways. Either after a certain time, that is commensurate with the lifetime of this metastable state, the electron auto-detaches, you've got autoionization, and then you have your molecule as you had it before, perhaps its internal state has changed. Or if the nuclei move fast enough, it might be that you get the molecule breaking up before the electron can detach, and therefore you have a breakup of the molecule in which the electron remains attached to one of the products of that breakup. So this is dissociative electron attachment, and this is a process that is very interesting because it is a chemistry initiator. In general, it will generate reactive species like anions or radicals and so on that will go, if they're in the medium, to interact with other molecules in the medium and give place to, for example, chemistry and other processes happen. The resonances are not only important because of dissociative electron attachment, they can also affect the size of the cross-sections for other processes. So the picture you've got on the right is experiments on vibrational excitation, and what you can see for certain specific angles, and what you can see is that where there are some peaks, these correspond to resonances. So dissociative electron attachment for H2 is a process that had been studied back in the 70s, but a few years ago, colleagues in India did some experiments that are called velocity slice imaging experiments. So what they could do there is they could send a beam of electrons of a specific energy to interact with the gas of H2 and then measure the H- that were being produced and in which direction with respect to the incident electron beam if the H- was being ejected. So you would expect that if this happens through the formation of a resonance, one can normally associate the resonance to the attachment of the electron to a specific orbital. So if you know the symmetry of that orbital, you can kind of predict, under certain conditions, the symmetry of the H- distribution that will be produced. And that is the case if you look here at 4.5 electron volts. So in this case, the electron beam is coming from down here. We've got the gas of hydrogen molecules, and what we'll see is that there's the same amount of H- that is ejected in the direction of the beam that is ejected against the direction of the beam. That is symmetric, and that can be explained because it looks like one of these orbitals. That's easy. However, when you go to 14.5 electron volts, what you get is that actually many more of the hydrogen minus can be ejected against the direction of the incoming electron beam than forward. And this asymmetry hadn't been seen before. It was surprising, and it wasn't easy to explain, because to explain it, you needed to understand what resonances were forming there. And people had studied H2 a lot, but they had not studied resonance formation in this energy range. So in my group, we set out to try to study these resonances. And what we found is that it's very complicated. So the experimental colleagues, E.K. Krishnakumar and collaborators, what they had hypothesized is that what you had at 14.5 electron volts was two resonances, that the electron can attach to either of these two resonances, and that the process of dissociative electron attachment through these two resonances interferes. And as whenever you have interference in quantum mechanics, in some cases you will have enhancement, and in some cases you will have quenching. And this is why we see H- produced much more in one direction than in the other. Now, for these to work, they did some kind of semi-quantitative simple calculations. And for this to work, they determined the resonances that needed to be there were of sigma G and sigma U symmetry. They determined what kind of energy difference they needed to have and what kind of lifetimes they needed to have. So we did very detailed calculations, not as good as the ones that I showed you before for electronic excitation, but we did very detailed calculations trying to identify the resonances of the sigma G and sigma U symmetry that would lead to this process, and we could not identify two resonances that had the right properties for this. And what we think at the moment, this is a paper we've got in preparation, is that actually the process is likely to be more complex. There is not just two resonances that are actually leading to this asymmetry there. Now, as we're talking about dissociative electron attachment and resonances, I want to show you another example. And resonances and dissociative electron attachment are important also in understanding this biological radiation damage that I was telling you before. Because it is known, and these experiments confirmed this more than 20 years ago, that when you have low energy electrons, these electrons can attach to the temporarily to the DNA. And if this happens, this can lead to breaks of the DNA strands. And if 2 or more of these breaks happen close enough, you can have DNA damage that the cell is not able to repair. So this is one of the mechanisms in which ionizing radiation can lead to cell death, for example. Okay. So people were interested in understanding how this dissociative electron attachment leads to DNA strand breaks. Now, studying the whole of a strand break or even a chunk is very hard. Computationally at the moment is really impossible from the scattering point of view. Experimentally is not easy either. So what people started doing around 15, 16, 17 years ago was to study electron interactions with the constituents of DNA. And in particular, people studied a lot the pyrimidinic nucleobases. So these are the nucleobases. This is for RNA, but this is for DNA. And you have here an the results of some experiment. So we wanted to do the same. This was more than 10 years ago, but these molecules have very little symmetry. And when you're doing computational calculations, symmetry is always your friend because it reduces the size of the calculation. So we thought, okay, let's start with something that we know or we knew at the time we could do well. Let's increase the symmetry by looking at pyrimidine. So it is in some sense, these molecules is the ring with the 2 nitrogens, but none of the bits that are hanging there, if you want. So we did a lot of work from pyrimidine. You can see here elastic differential cross sections, and you can see in here the electronic excitation cross sections. But the problem at the time was that there was no experiments. And then for us, these were the biggest molecules that we had been able to study with the R-matrix method. I have to say with the Shingle multi-channel, we see the potential you can do bigger systems than this. But for us, this was a big challenge. And we did not know whether we had a good agreement with experiment or we would have good agreement with experiment or not. And we were very lucky that a few years after we did this work, a colleague in Switzerland performed what are known as electron energy loss experiments. So what they do in these experiments is they start with the beam of electrons that have a very defined energy with a small energy spread, and then they detect the electrons after they've interacted with molecules. They can detect in which direction they have gone, but they can also detect how many energy the electrons have lost. The energy that the electrons have lost must have been deposited in the molecule. So you know that if that energy was deposited in the molecule, that means that there is an excited state, which could be electronic in this case, but could also be vibrational, that has that energy difference with the ground state. So in this way, they can measure electronic excitation cross sections, which will also show you the presence of resonances. Now, in the case of pyrimidine, this molecule has a lot of states, and this is what the picture on the left shows you. These numbers here in black at the top and the bottom are the energies with respect to the ground state of the different excited states. So in this case, you cannot, they could not measure the excitation into specific state, but bands of states, groups of the states that are close together. And this is what is shown on the picture here. The cross sections that they measured were for these different bands. So what we had to do in terms of the theory is to add up the states for each of these bands and compare with experiments. You can see the results in these pictures here, for band 1 and band 2. And the red jagged line is the experiment, and the black line in both cases is the calculation where we've added up the states that are involved in that band. So in this case, there's 2 things to note. First of all, that the size of the cross sections is more or less the same. So without normalizing one to the other, we got cross sections that are of the same size. This was already fantastic. We were really happy with that. But the other thing to note is that the shape of the cross sections is more or less the same, but shifted. So you can see that where the peaks appear in the red curve in the experiment, similar peaks appear, but a bit higher in the calculations. And we can explain that. We can explain why these peaks that are resonances appear slightly higher. The problem here is that the position of these resonances, the energy at which these resonances appear, is very dependent on the description of the polarization of the molecule. The description of how the charged electron distorts the electronic cloud around the molecule. And for these molecules that are very polarizable, we have problems in the method to describe polarization well. So when we don't describe enough polarization, the resonances appear somewhat higher in energy. But the experiments confirm the presence of 7 of the core excited resonances that we had seen. So these gave us a lot of confidence that even for these molecules that have 42 electrons, we can do calculations that are quantitatively accurate. Now, I've told you about these and about the the interest in terms of biological radiation damage and so on. But the reality is that if you want to see how electrons interact with molecules in the cell, the electrons are not isolated, are not in the gas phase in the cell. They're surrounded by other molecules, in particular by water. So one of the questions that people started asking themselves is, okay, how does this environment, the presence of these other molecules, affect the collision? And particularly, how does the presence of water do this? And you've got an example here of some experiments performed by colleagues in the Czech Republic, in Prague. You can see the results here on the right. And what they looked at was uracil and thymine, so nucleobases, surrounded by a few water molecules. So the water molecules tend to hydrogen bond to the molecule. Here's an example with thymine. And they didn't know how many molecules of water, but they knew they had one nucleobase and a few water molecules. And what they saw was this. When they looked at dissociative electron attachment for uracil, just uracil in the gas phase, the anion that was produced the most, this big signal here, was uracil with a hydrogen lost. Okay, so it's uracil minus hydrogen, and that's what they got. However, when they hydrated the uracil with a few water molecules or a few more, they cannot say how many, but in one case is more hydrated than the other. That signal, that anion, the uracil minus hydrogen, is not produced at all. So that process is completely quenched by the presence of the water molecules. And a couple of years, I think, after this experiment, colleagues then in Northern Ireland show that the reason why this is not produced is because the presence of the water molecules hinders the dissociation. So we know from experiments that the environment can affect the processes, but how else can it do? Can it lead to things that may not happen if you don't have the environment? Well, in fact, yes. And this is what are known as environment-assisted processes. So you may have heard about interatomic Coulombic decay, but I'm going to tell you about one that is related to electrons. So imagine you've got an ion, cation, immersed in a nanodroplet of helium. These can be produced, and they're produced in the lab if you want to model cold environments. So because the ionization potential of neon is about 3 electron volts lower than that of helium, you will not have a spontaneous transfer of an electron from one of the helium atoms to the neon plus. However, imagine that you have an electron coming in, a projectile, with a kinetic energy that is higher than this 3.03 eV difference of these ionization potentials. In that case, when the electron attaches to the neon plus, it's going to release the ionization energy and the kinetic energy that it has. And then the energy will be sufficient to ionize one of the helium atoms, and what you will have is a neutral neon in a helium nanodroplet, but one of the heliums is positively charged. And this is the process that is known as interatomic Coulombic electron capture. This was a process that was predicted in 2010, and Goldberg and Ziderbaum came up with an asymptotic expression, with an expression to provide a value of the cross-section where the distance between the cation and the neutral, say between the neon and the helium, is large. Now, we thought we could do better with the R-matrix method, because if you think about it, this ISEC process, which is here listed here, is basically like an inelastic scattering. You start with an electron of a certain energy, it interacts with the target, the internal state of the target changes, and you end up with an electron with a different energy. So we started by looking at this with one helium atom, and we did some fairly simple calculations with just a few states. And what we got is this. First of all, if you look on the right, what we've got here is for two scattering energies, we've got the cross sections for different distances between the helium and the neon. And what this shows is that when the distance is large, the asymptotic formula that is given by the lines gives results in agreement with the better R-matrix calculations. But as expected, as the distance between the helium and the neon gets smaller, there is more of a difference between the asymptotic formula and the more accurate calculations. And in this case, the more accurate calculations give bigger cross sections because they take into account the exchange and the correlation. The other thing we did is to then use these cross sections for one neon and one helium atom to model what would happen if you have 20 helium atoms, if you really have a cluster surrounding the neon plus. And when we did that, we calculated the cross sections for a few energies, and what we found out is that the cross sections are basically 2 orders of magnitude smaller than the elastic cross sections. And this ratio is basically the same to that you get between the inelastic, the electronic excitation cross sections, and the elastic cross sections for pyrimidine, for the molecule that I showed you before. So what this tells us is A, that the cross sections are significant, because if electronic excitation is significant, so is Isaac. And second, that in principle, if you use electron energy loss, you could experimentally try to measure these cross sections. Now, of course, a helium nanodroplet is not something that occurs very naturally. The thing that we are more interested in is what happens, for example, in water. So we also did calculations where we had a proton with one water molecule in this kind of configuration. So we changed the distance here of the proton. And in this case, you don't need additional energy, in fact, to transfer the electron for water to the proton. That state, the initial state, is above the lower, the hydrogen plus H2O plus, the lowest of those states. So again, this exemplifies the Isaac process. And what we saw in this case is that, again, we see cross sections that are large, but instead of being smooth curves, so here you have an example of neon with hydrogen, instead of being smooth curve, we see structure, and this structure corresponds to resonances. So there are resonant contributions to these cross sections. And the very interesting thing is that with some analysis, we found that some of these peaks actually correspond to resonances that are formed, not when you have hydrogen and H2O, but when you have hydrogen minus or H2O plus, or hydrogen plus or H2O minus. And this is really surprising, because these states form, these require the transfer to the movement of 2 electrons, and these states form even when the proton is about 10 atomic units away from the water. Again, unfortunately, there are no experiments for this. So I think I've got a bit of time, because I've gone quite fast. And before I finish, I wanted to show you something else. I mentioned to you that once you develop this kind of methodology and the software, you can use it for other things. And one of the things that can be used for is photoionization. So if you think about photoionization, in some sense, photoionization is half a electron scattering process, because you start with something and then you have something plus an electron in the continuum. Now, in this case, that means that the methodology that we've got can be used to produce the data that is then used to calculate cross sections for photoionization. In fact, the way we see it when we do this is that we treat the photoionization in some sense as a collision of the electron with the cation, if what we want to study is the photoionization of the neutron molecule. And I'm not going to go into the details, but the way this can be done is because you can calculate the dipole, the transitional dipole moments that one needs to calculate the cross sections using the R matrix basis functions that I mentioned before. So what kind of things we can do with this? Well, we can do things like, for example, study photoionization. So this is the case of photoionization of water, so single photoionization. And you can see the results here. Our results are the red curves, and there are a lot of experiments and there are the theories, and the agreement overall is very good. But we can actually also study more complicated processes. So processes like, for example, ionization by several photons. And when you do that, one of the things that you may be interested in studying is the time delay process for the ionization. Is an experimental method called Rabbit that has been used over the last few years quite a lot. And my colleagues, former students and postdocs of mine, Zdeněk Mašin and Jakub Benda in Prague, developed an approach using the time-independent R matrix approach and the software that we got to study these time delays and compare it with Rabbit experiments. And you can see here, this is an example for carbon dioxide, where you can see the 1 photon and the 2 photon processes. So you can see the time delays as a function of the XUV photon energy. And you can see that the agreement is quite good. But not only we can study this, but we can also study strong field processes. So these are processes where you can no longer use time-independent approaches. You need to use time-dependent approaches, so you have a strong field, a short pulse, interacting in this case with water. And in this case, we have to use our methods and codes together with an implementation of the R-matrix method that is time dependent. And if we do that, we can get, for example, things like the ion yields. So the yields that are produced when one ionizes the molecule, water molecule, and leaves the molecule in the different cationic states, the ground and the excited states. And these curves here show, depending on how good your calculation is, it shows you in which direction the electrons are ejected. So I'm coming to the end of my presentation, and I want to summarize what I've told you, and I hope I've managed to explain that, you know, we can do a lot, and there's a lot to do when one studies low energy electron molecule collisions, that we've got methodology and software that we can exploit to provide data that is needed in applied fields, for example, medicine, plasma physics, etc. That there are processes that we can't model that well. So things like dissociative electron attachment, things that involve resonances and nuclear degrees of freedom, which I haven't talked about very much, where we still need to do more work if we want to both provide an understanding of the process, but also quantitative data. Then again, the effect of the environment is something that needs to be studied a lot. And I mentioned this ISEC process. We have no experiments yet, but we're hoping that in the near future we might have some experimental results. And finally, I tried to give you a little flavor that once you spend time developing methodology and approaches like these, one should then try and exploit these to help with the modeling of other processes, of related processes in atomic and molecular physics. And before I finish, I want to mention the people that have done a lot of this work. It's not just me, of course, so the people that did the calculations for H2, the photoionization calculations, etc. And my colleague Nicolas Sissoura in Paris, who is the person that brought me in to do the work on the ISEC process. And of course, I mentioned a lot that we've got software that we use, and this is not software that we developed in, 2 or 3 people. It's an effort of several groups, both in the UK and nowadays also in the Czech Republic with Zdeněk and Jakub. And thank you for your attention.
Thank you, Jimena, for this very nice presentation. I'm not from the field, and I really learned a lot, so it was pretty nice. Thank you.
Thanks.
And now we can open for some questions. So before I just open for someone if wants to talk, or if someone is too shy to speak, you can write in the chat, or you can speak in Portuguese. And if Jimena doesn't understand, I can try to translate. So you can do something like that. So questions. Okay, so Pedro, yeah.
Hi, can you guys hear me?
Yes.
Yes.
Oh, hi, Professor Jimena. Thank you very much for your presentation. It was really nice. I got a question when you mentioned the resonances in pyrimidine, I guess it was pyrimidine. You mentioned that you guys saw a couple of core excited shape resonances.
Yes.
My question is, how do you characterize these resonances? You only look at a cross-section, or you do any additional calculation or additional analysis to make this characterization?
Okay, so we do additional analysis because you can have resonances that don't show in the cross-sections, and you can have peaks in the cross-sections that are not necessarily resonances. Yeah. So what we do in fact, trying to characterize the resonances is an art, and we've done a lot of work in my group trying to improve this, and I have to say with mixed success. So the default thing that we do is we calculate the eigenphase sums. So we get the K matrices and diagonalize those and look at the eigenphase sums, because the resonances should be seen as jumps of pi, plus the background on the eigenphase. So we use that. When you have a lot of resonances and you have dipolar molecules and things that are complicated, it's sometimes very difficult to see these jumps of pi. So something else that we do is we calculate the time delay. Okay, so there's a paper from the 60s from Smith that shows that you can calculate the time delay Q matrix using the derivative of the S matrix with respect to energy, and that the resonances would appear as Lorentzian peaks in the eigenvalues of this time delay matrix.
Mm-hmm.
So we do that, and the advantage of this method is that in principle, because you have to look at the different eigenvalues of the Q matrix, of the time delay matrix, it tends to separate the resonant and non-resonant contribution. So this helps. Now, but it's also not, it's not foolproof. We've also tried to look at the S matrices as doing sort of extrapolations of the S matrix into the complex plane, which has had mixed results. And my colleague Zdeněk Machine has a method which he's probably about to publish or has published recently, trying to determine significance of the resonances. So all of these methods can be used to find the energy and the lifetime of the resonance. Now, was that your question, or do you want to know how I decided its core-excited shape instead of something else?
Well, that was my question, but now that you mentioned, how do you decide it's a core-excited shape or a Feshbach resonance or anything else?
Okay. So this is a more ad hoc process. So there's various things you can do in some sense. First, you look at the energies of your target states, and sometimes it's kind of fairly straightforward. You've got a target state that is just above it and nothing around, and then it is quite likely that it is Feshbach. The other thing to do is we do, for example, comparisons to know whether they're shape or core-excited. We do comparisons of static exchange gas polarization calculations, with close coupling calculations, or we can do calculations removing some states, or and adding some others. So it's a question of comparison. There isn't an algorithmic. It's not a numerical way of doing this. Which is you have to see how they behave, these resonances, with respect to changes in your model. And then you can decide whether these are core-excited or Feshbach or even shape.
Yeah, it makes sense. Thank you very much, Professor.
Thank you.
No, thank you, Pedro, for your question. So next question, please. Yeah. So yeah. While you wait for another question, I have a question for you, Jimena. So you mentioned in the end that you are considering also like these, the effect of environment. So you are considering these molecules like in water. So you should consider also like the water molecules around your molecule and how it changes like the interaction with the electron. And so my question is like, have you? Okay, it's important to also think about like, let's think more real experiment when you have some dirt or some imperfections in your water, like if you don't have only pure water, but with different atoms or molecules also there. So,
in fact, you're right, because although living things are mostly made of water, they're not made of just water. In the cell, you've got water and you have other things. And this is in part why we were looking at this proton in water in ISEC, because in cell environments, and don't ask me too many details because my biology is not very good, particularly at almost 9 o'clock at night here in the UK, but you also have cations and you've got other things. So you're right. And if one wants to do something, actually one would have to have a mix of things. But we're trying with this, just putting some water molecules, and it's not just myself or the people in Prague doing this, the people in Brazil looking at these things as well. What we're trying to do is to try to bridge the gap between what we know in the gas phase and what it actually happens in the condense phase. Okay, so little by little. So perhaps, yes, you put 2 water molecules or 5 or 10, and then you think, well, what if I put a water molecule and a little something else? But yes, but it starts, it starts to give us an idea. This experiment that I've shown, where you see the quenching, this was very nice. This was something very nice, and it was unexpected because we did, people didn't think that it was obvious that something was completely going to disappear, some product was completely going to disappear. So we're developing the understanding little by little, and I have to say, having fun as well, because I find these things, interesting to study.
Oh, nice. Yes, thank you. So next question. Yeah, I think our students are a bit shy, I think.
Let me ask
okay, I understand that.
Yes,
Can I ask a question?
Yes.
Jimena, you didn't mention here in the talk, but we met last year at a virtual conference, and we talked a lot about positron sketching. Have you done anything lately to the best of our knowledge to improve the comparison?
So no, I mean let me explain this, Sergio. We've tried things to improve the comparison with experiment, and we have failed to improve the comparison with experiment. So I think you and I talked about comparison with the experiments of James Sullivan and his people at ANU.
Yes.
And at the time we were looking at pyrazine, which is one like this pyrimidine. I'm telling the other people is like this pyrimidine molecule, but is actually it has no dipole moment. We've got some here, that one there. And the agreement was poor then. And we tried all sorts of things with our matrix method. We tried to increase, we thought it was perhaps the description of polarization, whether we were getting the virtual state there right or not. We threw everything we've got at it, big calculations, bigger calculations, even bigger calculations. It makes no difference. It makes absolutely no difference. So either that is not the problem, either, there is something else, there is something that we don't understand of what those experimental cross sections are about, I think, or this is the limit of these kind of low energy ab initio approaches, and you need to do something else. The person that has been working on positron scattering from molecules is Dermot Green in Belfast, who you might know. And I think he's got a Nature paper coming on positron attachment to molecules, which I don't know more about. I just know that, but I'm very much looking forward to reading that paper and seeing what he has done, because he's coming at it from a different angle, not from the scattering, as we do, many body stuff and so on. So there may be something interesting, very interesting there, and perhaps that is a way that tells us something about perhaps where, certainly in the matrix, what it is that we're missing.
Okay, thank you. I'll keep an eye on that article also.
Thank you, Sergio. So do you have another question? I don't, yeah. Okay, so then maybe you can end our session, because Jimena, you can enjoy your holiday. So thank you so much for your talk. I think all of the students and all the audience really liked. It was very, very didactic. I think that's pretty great. So we are very pleased that you accept our invitation. And also, I would like to thank all the audience to be here and watch this very nice talk. So thank you, Jimena, once again, and have a nice holiday.
Thank you. Thank you, everybody. And hopefully I'll see you face to face someday.
Yes,
Have a good afternoon. Bye.